So, lecture 55, E equals mc squared. So this should be an interesting lecture. I could have renamed it m equals E over c squared. Probably would have been a better label for it, because that's really the point behind what I want to talk about today. In the last lecture, we demonstrated that the conservation of momentum and the conservation of energy don't hold up in the platform frame, right, of this collision that we set up on the train, right?
Yes.
And so we were assuming the train was going at some relativistic speed, so it's going fast, close to the speed of light. And you do this experiment with balls colliding on the train. And on the train, of course, everything is conserved. It's an elastic collision. But in the platform frame, when we just simply do the coordinate transforms, right, to see what does it look like in terms of our rulers and our clocks, we get that energy and momentum were not conserved. And that doesn't make sense. Laws of physics should be the same in all reference frames. That was one of the fundamental tenets of the principle of relativity. So we should find that energy conservation and conservation of momentum should be invariant. And it wasn't. So we need to find something that is invariant. And if we go back to lecture 53, I believe, we had actually discovered an invariant, right, the way that we measure distances in space-time, which looked a little bit like the old Pythagorean way of doing things, right, where we take the square of the x distance squared plus the y distance squared, right, will give us the length of the line between those 2 points. But it had a minus sign in it, so it was a little bit funny. And just to remind you, it looked like this. Delta tau squared equals delta t squared minus delta x squared. This we found was invariant, right? This is some kind of measurement of length or distance, if you will, in space-time. It has both time and space in it. And this is invariant between reference frames. So if I were to, for example, this will also be equal to delta t prime squared minus delta x prime squared, you see?
Yes.
It doesn't matter if I'm using the rulers on the train and the clocks on the train, or if I'm using the rulers on the platform and the clocks on the platform. This number will be the same, okay?
Okay.
And that's important. That's what makes it invariant. It doesn't vary when you go from reference frame to reference frame. So it sounds like exactly what we're looking for, okay?
Okay.
So the technical derivation that I'm going to try to present to you guys today usually requires a minimum calculus, and we don't have calculus. This is an algebra-only course, so we can't do it that way. Typically what we do is we would recall that the kinetic energy is going to be equal to the force times the distance, and we do what's called an integral, which is a kind of a continuous sum over all the different positions along the way as this force vector moves some distance. But we're not going to do that. At a higher level, we might resort to something similar to the principle of least action, which is like the principle of least time that we talked about earlier in the course as it pertained to light. But these are higher math tools. We don't have them, so we're going to do something kind of cheesy, okay? And we're going to cheat a little bit. But we'll get there. So it'll be fun. But let's manipulate this just a little bit. I'm going to erase this part. Now the first thing I'm going to do is I'm going to take the square root of both sides. So I get delta tau is equal to the square root of delta t squared minus delta x squared. Now I'm going to divide out the delta t squared. Okay? Just going to factor it out. This will be equal to, you can just see that we have a delta t squared, 1 minus delta x squared divided by delta t squared. In here, you see that? All I did was just factor out a delta t squared. So if I multiply this through, it puts everything back as it was. Okay?
Okay.
You'll remember one of the qualities of factors underneath the square root sign is that you can pull them out. So delta t squared, right, this is just equal to delta t times the square root of 1 minus, I'm going to put this in parentheses, delta x over delta t squared, right?
Yeah.
Now, delta x over delta t, that's a distance divided by time. What do we call a distance divided by the time taken? If I say my car traveled speed or velocity, right? So since we're in one dimension, we're either going in the positive or the negative direction, so it's a velocity in this case, we'll call it. And so we can rewrite this as delta t times the square root of 1 minus the velocity squared. Now this should be interesting to you because you'll recall that when we did the Lorentz transformations, we had this thing that we called gamma, which got multiplied through the transformation equations. They look very similar to the Galilean transformation equations, except they had this gamma. And that was 1 over the square root of 1 minus the velocity squared, right?
Yeah.
We're about to see what that means right here. So, almost where I want to be. I want to now divide both sides by delta t so that I get delta tau over delta t is equal to 1 minus v squared. And then the last thing I can do is I can flip everybody, right? So it's going to become delta t divided by delta tau is equal to 1 divided by 1 minus v squared. There's your gamma. That's equal to gamma. So gamma all along, what is it, right? It's this kind of weird measurement about it's like the change in clock time versus the change in proper time. So it's the rate at which clock time changes per change in proper time. Remember, proper time is time measured by clocks that are stationary with respect to the reference frame, right? Yeah. So they're times that you measure always at the same position, okay? So if I measure the interval between two times, but I'm measuring them at the same place, then that is what proper time is. But the easy way to think of it is it's where the clocks are moving with the frame that you're making the measurement in, okay? As opposed to taking a measurement of, at one time in one position and then at a different time in another position, right? As we did when we saw the train passing by. This, of course, leads to these bizarre effects like length contraction and the time dilation that we talked about. All right, so here's our first one. I'm going to just write this over here. I'm going to write it. Delta t over delta tau is equal to 1 over the square root of 1 minus v squared, which, of course, is what we call gamma. Now I'll remind you that if you wanted to put units back in, right, the way to do it is, you see this is unitless, this 1, and we're going to subtract a quantity which has units of meters per second squared, both of them meters squared per second squared. So to make the units right, you could divide v squared by c squared, okay?
Okay.
All right, so that's where we are at that point. Now I want to go back up here as follows, okay? And I want to introduce this a little differently. Now what I'm going to do is I'm going to divide both sides of this equation by delta tau squared. So I get 1 equals delta t squared divided by delta tau squared minus delta x squared divided by delta tau squared. Delta t squared divided by delta tau squared, this is just gamma squared, right?
Yes.
This is some kind of, it's like a funny velocity, it looks like, right? But it's not quite a velocity. This delta x over delta tau, right? It's the distance traveled divided by the proper time, okay?
Okay.
So it's not quite the velocity, but it's related to the velocity. And so I'll do a little bit of trickery to show you how it's related. The velocity, oh, that's funny. The velocity, right, this velocity right here, remember that was delta x over delta t, right? Delta x over delta t, right? And I'm going to do the fun math trick where I just multiply by 1, because it doesn't change anything, right? So I'm going to multiply this by 1, delta tau divided by delta tau, right?
Yes.
I haven't changed anything. I'm just multiplying by delta tau divided by delta tau. That, by definition, is 1. But what I'm going to do now is I'm going to exchange denominators, okay? So this is delta x over delta tau. You might recognize that as the quantity of interest here, right? And then I get delta tau over delta t, which we see as our 1 over gamma, right? So this gives me, so delta tau over delta t, that's just the inverse of this, right?
Yes.
That's 1 over gamma. So that's 1 over gamma times delta x delta x over delta tau. Yes?
Yeah.
And so now I can solve for this, delta x over delta tau, try to make that a little nicer, tau, there we go, is equal to gamma times velocity. You see that?
Yeah.
So I think I want to put that in here, gamma squared, minus delta x over delta tau, that's gamma v. So I guess I could just write it as gamma squared v squared. All right? Gamma squared v squared. Okay? Now, of course, you have to know where you're trying to get in order to do it. You don't think, oh, how in the heck is he coming up with these ideas of what to do next? Well, I know where we're trying to get. Okay, that's why we're kind of cheating a little bit, right? It's not like I set out a problem to solve and this is how you get the solution, right? I know where we want to be, which is why I'm doing the things that I'm doing so that we can get there, okay?
Okay.
Now, everything here is still invariant. Remember, this is an invariant equation, so this is still invariant, okay? What I'd like to do next, right? If I have an invariant quantity and I multiply it by another invariant quantity, Is the product invariant? I mean, for example, temperature, right? That's a scalar quantity, right? The temperature in the room at a certain position is a scalar quantity, and it is invariant between coordinate systems. If I measure the distance to the point at which the temperature is 100 degrees, right?
Yep.
If I measure it with yardsticks or meter sticks or, foot-long rulers or centimeters, it doesn't really matter. If I measure it, if I put it on a train and I allow it to go past me at some speed, it's a scalar. It's not going to be different if I measure it in a different coordinate system, right?
Yeah.
What is the temperature of, a hot coal if I run past it really fast? It's still the same temperature. It doesn't change. Scalars are invariant, okay? And so mass is a scalar, right?
Yeah.
It's not a vector. It doesn't have a direction or anything like that. It's just a scalar, and so it will be invariant. And so if I multiply this invariant times another invariant, the product will be invariant. So another invariant, if I multiply this entire thing, instead of mass, I'm going to multiply it by mass squared, right? Let me just write mult by m squared. We'll get m squared, because 1 times m squared is m squared, equals gamma squared m squared minus gamma squared v squared m squared. Okay? Then you're thinking, well, gosh, what's the point of this equation? What does this mean? It's invariant, yes, but does it mean anything? Well, in fact, it does. If we look at this right here, what was the definition of momentum? Anyone remember? We give it the label P for the German word Pumpkenflargen, I guess. And momentum is equal to the mass times the velocity, right? Yeah?
Yeah.
So that's the definition of momentum. It's one of the things we were looking for conservation in, right?
Yeah.
See the m and the v here, right?
Yeah.
We can rewrite this as m squared equals gamma squared m squared minus gamma squared, and then v times m, or m times v, well, that's just momentum, right? So this is just p squared, momentum squared. Okay?
All right.
Because it's the mass times the velocity, you see?
Yes.
Squared, both of them, right? Okay, so let me write this down over here. M squared equals gamma squared m minus, and I'll just write it like this, gamma p quantity squared. And let's try to understand what this term is. But in order to do that, I have to remind you of a little bit of an approximation trick. Okay? If you're familiar with the binomial theorem, then you know this trick, but let me just demonstrate it just in case you've forgotten how that works. If I consider the equation x plus y squared, right? If I multiply that out, the first term will be x times x, right?
Yeah.
We usually write x squared, but there's a reason I'm writing the symbol separately. Plus x times y plus y times x plus y times y, right?
Yes.
This, of course, is the leading term, right? Notice that this xy plus yx, right, we can kind of bring that all in and write that as 2 times x times y, right?
Yeah.
Because x times y and y times x, they commute, so they're the same thing, so it's just 2 times x times y, right? And if y is small with respect to x, right? So imagine that x is like, I don't know, 10, right? So we've got 10 squared, that's 100, right?
Yeah.
The next term, right, 2x times y, well, that's 2 times 10, or 20, times y. Let's say y is 1, right? So that's 20. And then finally we get this last term, y times y, well, that's 1, right? So I get 100 plus 20 plus 1, right?
Yeah.
These first 2 terms are kind of the big terms, right? So I can say this is approximately equal to just the first 2 terms, and I can throw away the last one, right?
Yes.
And so that would be the x squared term plus the x times y term. Yes? Well, it's going to be 2 times x times y. Yes?
Yeah.
Okay? If we do the same thing for x cubed, x plus y cubed, the first term will be the x times x term, right? That'll be the leading term. The next term will be, we'll have 2 x's and 1 y, right?
Yeah.
2 x's and 1 y. And I'm not going to do any more terms because we're going to make the same approximation. Let's say y is small, okay, compared to x. And so I only want to keep the first two terms, the bigger ones, right? This is the one that has x cubed, this is the one that has x squared, right? Making it big.
Yeah.
But I need a coefficient here, right? And so the number I put in front of this, right, is, well, I've got x, x, y. How many ways can I rearrange x, x, y? Well, there's x, x, y, there's x, y, x, and there's y, x, x, right?
Yeah.
That's three ways, right? Another way to look at it is, if I think of this as a word, and I want to know how many ways I can rearrange the word, right? This is equal to 3 factorial. That's the number of ways I can rearrange the top, and then we divide out 2 factorial. That's because of the two x's, right? So 3 factorial divided by 2 factorial, that's 3. So the coefficient that goes in front of here is 3. So this, right, is approximately x cubed plus 3x squared y. This is the important part, okay? It turns out that you can show that x plus y to the nth power is approximately equal to x to the nth plus n times x to the n minus 1 times y. Okay?
All right.
So that's important. All right, so we can use this result, this approximation, to rewrite 1 over the square root of 1 minus v squared, which is equal to 1 minus v squared to the minus 1/2 power, right? This will be approximately equal to 1 minus times a minus 1/2 times v squared, right? Which is 1 plus 1/2 v squared, okay? So I'm going to approximate that square root that has the velocity in it using this scheme that we got from the binomial theorem. And I'm going to use it to re-express gamma m, right? So gamma m, this term right here, right? What is this term? That's what we want to know, okay? This term is equal to m divided by 1 minus v squared, yes?
Yeah.
Which is equal to m times 1 minus v squared to the minus 1/2, which is approximately equal to m times 1 plus 1/2 v squared. Okay? So gamma m is approximately equal to, I'm going to just distribute the m plus 1/2 mv squared. Okay?
All right.
Now, if I were to put units back in, okay? Remember when we put the units back in, because we set c equals to 1, right? To get the units right, we have to put the c's back in. And we can see that what we need, since these two things have to be have the same units, right? We need a velocity squared multiplied by this over here. And since the thing we always put back in is c, we'll multiply it times c squared, right? So I'll write mc squared plus 1/2 mv squared. Okay? So this is the case where c is equal to 1. Here I'd let c be something, be the real value, right? Do you recognize 1/2 mv squared? All right, what is that? Kinetic energy, right? T is equal to 1/2 mv squared, right?
Yes.
This is the kinetic energy. So if this is the kinetic energy, then we suspect that this must be the kinetic energy. Okay?
Okay.
This is what we call the classical limit, right? So as the velocity is very small, right?
Yeah.
Not close to the speed of light at all. In our case, right, it means that v is a number like 0.01 or something like that. 0.1 is even big, right? Because 0.1 means you're going 10% the speed of light. There are relativistic effects at that speed. But we're assuming it's really small, so this is the non-relativistic limit. And in the non-relativistic limit, we expect whatever this thing is, this gamma m term, right, it should have some correspondence to something in classical physics that we know of. And we know what that is. That's the kinetic energy, okay?
Okay.
This thing here, right, well, we haven't seen that before. What is this thing? And I'll just, tell you, this is what we call the rest mass. You can see why it's called the rest mass, because if v was 0, this would be the term that remains. You can kind of think of this as like potential energy, okay? And when we have the potential energy and we add it to the kinetic energy, we get the total energy, okay?
All right.
And I'll explain why I say you can think of this as the potential energy in just a minute, okay? But we're going to think of gamma times m as the total energy. So this is the total energy. This is the rest energy, or potential energy if you would like. And this term here must be the kinetic energy. if we call total energy E, right, then that would be E squared equals mc squared plus gamma squared p squared, right?
Yep.
These arrows apply to both sides, okay? Let me just do some... Well, I guess the interesting thing about this is the rest energy, okay? If I put some potential energy into the system, right, it's going to manifest itself as a mass. So let me give you the following consideration. Here is a scale, and let's say it weighs, 10, or make it 100 grams. What is it that weighs 100 grams? This little spring that I've got that is at its equilibrium separation, so it's an uncompressed spring, and I put it on the scale and it weighs 100 grams. What do you think a compressed spring weighs? And I'm going to let it be compressed. As it turns out, it's going to be a little bit more. The fact that I compress the spring is actually going to make it weigh a little bit more. Now, it's a very small amount, mind you. The potential energy, which we haven't really talked about for a spring, is equal to 1/2 kx squared. I can calculate what the potential energy is, similar to with gravity. Right? With gravity, at the surface of the Earth anyways, the potential energy is mass times g times h, the distance I raise it. This is similar to that. It's 1/2 kx squared, where k is the spring constant. And so we can write E is equal to m naught plus this 1/2 kx squared part. I'll have to divide it by c squared, but then multiply it times c squared. P is 0 because my spring is not moving; it's just sitting still. Okay, so a compressed spring actually weighs more. It gravitates, right? It actually gravitates.
Right.
Does that make sense? That means that things are attracted to it gravitationally. Okay.
Okay.
So this will have real consequences with nuclear physics. It is behind the reason why the atomic bomb releases such a tremendous amount of energy. Okay.
Wait, I didn't understand the part where things gravitate towards a spring.
Yeah, well, we'll get to gravity soon. I think next week we're going to do just a little bit of particle physics where we'll talk about the fundamental particles like protons, electrons, and neutrons, photons, and gluons, and other basic particles. Well, we'll use this actually to discuss it, okay?
Okay.
Because this is actually very useful for that stuff. But we'll find there are 4 fundamental forces. One of them is gravity. So you're familiar with gravity. We've talked about it in the context of kinematics and in terms of Newton's laws of motion, right?
Yeah.
But we have yet to talk about Newton's gravitational law, okay? Where he finds that a body of a given mass, right, has a gravitational attraction to objects near it, right? And how near? Well, it obeys a 1 over r squared law.
All right.
And so we'll find this law of physics that Newton found. It's a 1 over r squared law, and it says that masses gravitate. They cause things to be attracted to it. Okay.
All right.
The details of that we'll get into soon. But the point is that the gravitational mass, the mass that's affecting gravity, is affected by the potential energy. So if you compress a spring or wind a clock, it weighs more. If you run electricity through a light bulb, the mass of the light bulb increases. Okay.
Okay.
Because we've energized it. If I were to somehow lift all the mountains and all the continents of the Earth and raise them off the surface up to some altitude, right?
Yes.
I would increase the gravitational mass of the Earth. It would change its orbit if you lifted enough mass far enough away. Now with gravity, these effects are very small. Okay. With most things, these effects are very small. Even with the electronic state of things, right? When I burn, strike a match, right? The mass before is actually larger than the mass afterwards. If I measure all the things that come out of it, right, the mass is not conserved, right?
Yes.
There'll be a little bit less. If I go to a power plant, regardless of what kind of fuel it uses, I will find that at the beginning of the month, if I weigh the power plant and all the fuel in it, it will weigh more than it does at the end of the month after we've generated all this energy, electricity and whatnot, right?
Yeah.
Some mass was converted to kinetic energy to do work. Okay?
All right.
And that's what this E equals mc squared business is all about. Okay?
All right.
But we'll see more specific examples of it, and maybe that's what it takes to really understand it when we talk about particles and stuff next week. But yeah. So we now have this kind of new model for conservation. I haven't shown you that this is conservation of energy and conservation of momentum all in one, but you can kind of see what it is because we can calculate an energy, the total energy of the system, in two different reference frames, and it'll be invariant. We have a way to do that now, okay?
All right.
And we'll see in the next lecture, and this will be the last of the relativity lectures, how we can use this new idea of momentum. Instead of just P, like we used before, what we needed to be using was gamma times P, okay? So we'll see how we can use this idea of a relativistic momentum to solve the conservation of momentum problem that failed us in the last lesson, okay?
Okay.
And we'll see that momentum is conserved in the platform. Momentum is conserved in the platform frame. All right?
All right.
And I think that's really all I wanted to do in this lesson. Unfortunately, this is not, a derivation in the sense that we kind of engineered we knew where we were going, and we knew a way to get there without having to use calculus and other higher forms of mathematics. But the general idea is there. Okay?
Okay.
All right.